Okay, I'd like to thank the organizers for inviting me. I'm actually not a physicist. I'm a condensed matter synthetic chemist, so it's quite a pleasure to speak to this audience. What I want to tell you about today is really a passion of mine, which is making new materials for applications in renewable energy. So I'm going to tell you about the battery that my group and I have been developing, and along the way I'll explain how we spun that out into a startup company. So I could have shown you a cell phone or a laptop, but this is my favorite battery-powered device. This is a Tesla Roadster, which is an incredibly fast sports car, which I've had the privilege of driving only once. I like to show this as an example, particularly in the United States, because there's often a misconception that electric vehicles can't be fast. And this car is actually very fast. It's faster than a Lamborghini over short distances. But the challenges that the battery pack in this car present are very similar to what you experience every day in your portable electronics. It doesn't last as long as you would like. So to illustrate that, here I'm showing the range of the car. It's supposed to be 244 miles on a single charge, but that's when the battery's new. As it ages, the driving distance becomes shorter, and in a very cruel twist of irony, the more aggressive the driver, the shorter that distance is. This is what I'm going to refer to as energy density. How long can you use your battery for a given charge? The other challenge in this particular vehicle is the assembly of the battery pack. So it's composed of cells that are very similar to the cell you would find in your laptop, but it's about 7,000 of them. And they're assembled basically in this model. It takes up the entire trunk of the vehicle. And the replacement cost of just the battery pack is about $36,000 US. And so to me, this highlights a very significant problem in this field, which is that if you're going to innovate a very useful battery, it really does need to be made at a cost that is allowable for everybody to use. So the challenge is really for the battery here is the driving range, which is energy density. It has to do with the charging time. A battery of this size takes between 12 and 16 hours to charge through the kind of outlet you would use, say, for a clothes dryer. And so for a lot of Americans, that's quite simply too long. The cost, as I mentioned, and then finally the safety. This battery has a very flammable liquid electrolyte, which is the same electrolyte you carry every day in your laptop or your cell phone. And so now in some states in the United States, if you get in a car accident in a vehicle such as this, emergency personnel are not allowed to try to remove you from the vehicle. They're supposed to wait for a hazardous chemical team to arrive, which is just simply not practical. So we've been thinking about ways to try to improve on this battery while still maintaining basic lithium-ion battery chemistry. So I want to explain a little bit about how your battery actually works so you can see the approach that we've taken. So in a typical battery, you have two electrodes, your cathode or your positive electrode and your anode, the negative electrode. In your cell phones, you have a cathode that's composed probably of lithium cobalt oxide or lithium iron phosphate. It has transition metal ions in it that are redox active. On the other side, you have graphite, and this is the side that lithium intercalates into when you charge your battery. So the lithium ions are stored between the layers of the graphite. They can then donate their electrons to go through a circuit to do work. They're deposited in the cathode, and then that will reduce a transition metal ion. So to maintain charge neutrality then, you have to have lithium ions migrate from the anode through some kind of an electrolyte to your cathode. It has been very well established that if you make nanostructured electrodes, you can charge and discharge your battery much more quickly because you're reducing the diffusion path through the solid, which is really the rate limiting step. The challenge, however, is in getting this high surface area electrode to be in very close proximity to the other electrode. And that problem really has not yet been solved. Okay, so a normal battery then, the ones you're carrying today, are what I'm going to call two-dimensional batteries. They're made of thick films that either get stacked or rolled depending on the form factor of the battery. And so the diffusion path is really dictated by the thickness of the film and then the physical distance between the two films. So in terms of the power density then of your battery, this is going to be dictated by the voltage, which you get to choose based off the chemistry that you choose for your two electrodes, multiplied by the lithium-ion conductivity, and that's determined by the slowest piece of your battery, multiplied by the interfacial surface area. So this is why high surface area is going to become very important. And then all of that is going to be divided by this characteristic lithium-ion diffusion path. So how close you can get those two electrodes to each other. What is important to point out is in a two-dimensional cell, you cannot decouple power density from energy density. So if you want your battery to last longer on a single charge, typically the power density suffers, and those batteries take much longer to charge. If you want a very high power density cell, you make very thin films, and then the energy density suffers. So you can't run the battery as long on a single charge. So this is the limitation of a two-dimensional battery. And so because of this, what we really wanted to think about was how to build a three-dimensional battery. Now, in a normal plot for a battery person, you would compare power density on the y-axis to energy density on the x-axis. Batteries tend to do very well in terms of energy density, but they do very poorly in terms of power. A device like an ultracapacitor does very well in power, but it's pretty poor in terms of energy density. And so what we and many other people are trying to do is develop a device that would be in the top right corner. So try to combine power density and energy density. And I put two references on here that I encourage you to read. Those really inspired my thinking in this field. I don't want you to get the impression that I'm the first person to try to build a 3D battery. The top reference from Deborah Rawlson's group at the United States Naval Research Lab is really a review of possible architectures for 3D batteries, although none of those have actually been realized yet. And then the bottom reference from Andreas Stein is the first, in my mind, approach toward trying to make a 3D battery using solution process steps. Although it also didn't, that device didn't store energy, but it really taught me a lot in terms of some of the challenges in this field. Okay, so when we began this experiment, it was a project that was designed to be a very rich project in terms of something that many PhD students, undergraduate students, and postdocs could work on. So I was not intending to start a company. So the goal was not to achieve this quickly. What we decided to do was to take a big step back and think about 3D batteries and some of the challenges that had been presented. And in keeping with sort of the goal of what I told you at the beginning in terms of cost, what we ended up doing is making a list of all of the equipment we were not allowed to use. So nothing that requires low vacuum, nothing that requires a clean room, nothing that requires very long processing at high temperatures. And then from that list, we came to electrochemical plating as a very inexpensive approach, a method that's very good for making materials. It's never been used for batteries, but it's very well known in industries like the semiconductor industry, high quality finishing on things like car bumpers and jewelry. And so we knew it could be scalable and it could be inexpensive. So once we decided to focus on the method of making the material, then we decided to focus on the architecture and make lists of physical properties for every piece. And that's how we guided sort of our approach in terms of the kinds of chemicals that we were going to use. My personal interest is also in the environment, and so my ultimate dream was to make all of these steps from water-based solutions on a benchtop using as non-toxic chemistry as possible. And very fortunately, my students have been able to actually make this happen. So the way that we're trying to approach building our battery is to use the copper foam current collector as the tool to build the rest of the battery, and it is what sets the physical dimensions of the battery. So we begin with a piece of copper foam. It's about 98% void space, so it's less copper than the current collector in your current battery. It has a very high surface area that's going to lead to very short ion diffusion path, and because of this geometry, we theoretically could achieve 5 times higher power density than what you can achieve in a two-dimensional structure. So we use this as our working electrode, then we directly electroplate our anode material. In this case, we had to choose something that could be directly electroplated, so we can't use graphite, which is the normal anode material. And I will tell you a little bit more about this compound in a moment. But what you need to get away from it is that it has a 3 times higher volumetric energy capacity than graphite. And more importantly, chemically, it's quite a bit safer than graphite. So it eliminates the potential of plating lithium metal, which is one of the major causes of shorts in current lithium-ion batteries. The compound that we use, copper antimonide, is also a very good metal. So we use this as the electrode to electrochemically polymerize our polymer electrolyte. And in this way, we can conformally coat our 3D structure. The challenges that have been plaguing people using other approaches in 3D batteries is that this electrolyte layer is typically an inorganic material that gets vapor deposited. So mechanically, it's very rigid, and it tends to fracture over time. Or they use chemically polymerized polymer electrolyte layers, which always leave pinhole defects, and those lead to shorts. So those devices typically behave like leaky capacitors. So our thought was that we'd use electrochemical methods to ensure truly conformal coating, still stay with a polymer electrolyte, which affords the mechanical flexibility that you need. But unfortunately, there were no polymers on the market that could do all of that. So we had to develop new materials that could function. And I'll show you that we've actually made some good progress at the end. We build in some safety in this step as well. The polymers we use are non-flammable, and that leads to increased life cycle. So we've eliminated the liquid electrolyte present, and we've also eliminated some of the supporting electrolytes that chemically are a bit hazardous. And then in the final step, we use inks of commercially available cathode materials. We've also modified this step so it is all water-based. Basically, you put your ink on your structure and it soaks it in, sort of like a dry sponge soaking in a liquid. And then you add your current collector and dry it at the end. So all of the steps now are water-based processing steps. They are all done on a benchtop, and I'll show you a picture of that in a moment. So the manufacturing cost calculations predict that whereas a normal lithium-ion battery can be made for about $500 per kilowatt hour, using this approach we should be able to get to about $200 a kilowatt hour in US dollars, so significant savings. So in terms of my research group in the academic setting, my students work on the very basic research that is much longer term, and it has to be work that can be published and that they can talk about in interviews. Whereas the company typically works on the more sensitive aspects of this. Their goal is really just to make a working battery and to file IP along the way. So that's how I try to balance sort of the professional development, both of the students in my group and the people that work in my company. Now, to show you just a cartoon of a cross-section, at the end, we actually use aluminum mesh current collectors, and I'll show you an electron micrograph image of what this looks like. And then to build up capacity, we just stack cells. And then if you look at a cross-section, you can see the copper foam, the anode material coated with the polymer electrolyte, and then with the cathode material surrounding it. And then we capacity match our cathode to our anode based off the geometric constraints of the substrate. It's a very fast process. This is part of why this is so expensive. So this is just an image of the copper foam with the current collector attached here. This is after about 90 seconds of plating of our anode material, and it's an active anode material as plated, so we don't need to do any post-processing. And we've been able to develop the methods to scale this process up and to build our full 3D prototype. Okay, so in terms of theory now, moving from the cartoon that I already showed you, now actually adding units. All of the chemistry I'm showing you here is actually real. It exists in the real world. These are measured values. Our value up here is calculated. So I want to be very clear, we have not achieved this yet. But based off the geometric arguments of our structure with conservative estimates on the physical properties of each layer, we should be able to achieve power densities near about 18 kilowatts per liter. And then in terms of energy density, we should be competitive with a lithium-ion cell, say one from A123. There is a very exciting breakthrough from a company called Envia. They demonstrated very high energy density, but I put a red question mark by that because apparently those results are not reproducible. So it's not clear whether or not they actually exist. But I want to show you that there are people working on trying to extend the x-axis of this plot. Okay, so in my group we were thinking about building this battery, but my university's been trying to really encourage faculty to start companies and to license their intellectual property. So what we needed to teach ourselves in my group was, what do people in the battery industry actually care about? And what they actually care about are these 6 metrics that I'm showing you here: cost, lifespan, energy density, power density, safety, and form factor. And so what I did is I put in this box here the 3 that I think we do best. So power density, we should be a 2x to 5x improvement over industry while maintaining competitive energy density. The safety is significantly higher. Our battery is very stable, including cycling under elevated temperature conditions. And then in terms of the form factor, what is I've now learned very unusual about our approach is that we can cut the copper foam to any size or shape that you need for your device. So as opposed to a traditional battery where you're limited in terms of the form factor, in our case we can make wedge-shaped batteries, we can make curved batteries, because the electroplating is the same. And so now we are trying to identify partners for whom the form factor is actually the important attribute. I just want to tell you a very little bit about the thinking in terms of the two main pieces of our battery, the negative electrode and the polymer. Again, just to show you where we came from in terms of academics moving into industry. Okay, so I told you we initially targeted a method of making the materials that we thought could help us target this architecture. Then we had to think about the actual compound. So what we did is we made a list of all the physical properties that were important, and we used that to help guide us toward the actual chemistry that we were going to use. So for the anode, as an example, it has to be something that can conformally coat a 3D structure. It has to be electrically conductive, thermally conductive. It has to have a high volumetric capacity for lithium. And it has to have a lithiation voltage that mitigates lithium dendrites. And so from these constraints, we chose copper antimonide as our target. The challenge, though, was that that compound had never been directly electroplated. And there were very, very few examples of compounds from this class that could be electroplated. So my very first PhD student was given this task. Fortunately, neither of us knew enough to know that this should have been difficult. And remember that my goal was water-based chemistry. So I asked him to develop a method to do this, ideally not using any toxic chemicals. And he was able to accomplish this by using citric acid as a ligand to shift the reduction potentials of the two elements. Citric acid is a very common food preservative and fortunately very, very inexpensive. So we can directly electroplate this compound. It has a very unusual property. The way this compound works is it begins as Cu2Sb, and I've circled 5 of the antimony atoms in red. Then it charges to form this compound, lithium antimonide, and notice that the antimony atoms don't change structure. So they provide a framework that breathes in and out as copper is extruded in lithium intercalates, and it is very reversible. In terms of capacity, in terms of gravimetric capacity, it's heavier than graphite, so the gravimetric capacity is not as good, but volumetric capacity is over twice as high. Antimony is not completely environmentally safe, although in this compound it is very stable, so it's not leached out of the compound. But unfortunately, we can't avoid using antimony because it's required for the physical properties of this compound. And what's important is that, again, it lithiates about 50 millivolts more positive than the plating of lithium metal, so it's quite a bit safer than graphite. This is what the structure actually looks like when you plate on the copper foam. This is a low resolution electron microscope image, a higher resolution image showing the areas of high curvature, and you can conformally coat it, again, very quickly, and then it's a working battery. So the first thing we had to learn in the company, which was very different from an academic group, is how to scale up our process. We started electroplating in 50 milliliter beakers, as is very common in a normal chemistry lab. Now we do these platings in 22 liter tanks. This is exactly the kind of tank that a company like Intel or Applied Materials would buy as their R&D electroplating line. And you could see just a series of very simple tanks, power control at the end. These are all just washing steps. You can see one of our little copper flags hanging here. We typically, for the form factor of a battery you would put into a smartphone, we typically do 12 at a time. But a line like this could very conservatively make about 10,000 cells in a year, just running one shift a day for 5 days a week. The reason we invested in this is because the method of making our battery is not used by any of the large battery manufacturers. And so we needed to be able to demonstrate to investors that we could at least accomplish the first step of scaling up this process, because it's not a direct line to license to a company like Samsung or LG without demonstrating that this works. Now what we've learned is that in the scaling up of this electroplating step, you actually achieve much better control over the samples and you get much better performance than you could ever achieve in small batches. Okay, so this is just to show you kind of the development and also to drive home the point that going from 2 dimensions to 3 dimensions brings a significant benefit. So in this case, the data, don't look at the plot yet, but just to describe, the data that I'm showing you is for assembling our copper antimonide anode electroplated, both onto copper foil, so 2-dimensional sample, and then onto a 3D foam. and then assembling the rest of the battery using conventional materials. So this is not a fully integrated 3D battery yet, it's just studying our anode. So what we're plotting here is discharge capacity as a function of cycle number, and this set of data here is from the copper antimonide plated onto a foil. So 2 dimensions, and you see that the discharge capacity is very low. That's because we're charging and discharging pretty quickly. We're charging at a rate of about twice what your cell phone will charge at, and in 2 dimensions the material just simply can't keep up. This is the data for coating that material with some of our advanced coatings that can help with the capacity, and they also extend cycle life. But now if you go to 3 dimensions, the 3D foam, you see a dramatic improvement in the capacity, but you see that the cycle life is still pretty poor. If we coat now with some of our advanced coatings, you see the discharge capacity is high, and with our most advanced coatings, our recent coatings, the cycle life stays very good. So again, the technology that came out of my academic group is the plating of this anode material, but then in the company we've developed coatings that are really geared toward some of the practical aspects of how you'd actually want to use a battery. So what we've learned as a company is that investment in energy storage in the United States right now is very challenging. There are many very prominent failure stories of energy storage companies that have gone bankrupt. So investors are quite leery of investing in a very long-term development project. So what we've done is we've taken what we've been able to develop for our anode and spun that out as a much earlier potential product. So what I showed you at the very beginning was this dream of a 3D solid state battery, and this is still the long-term vision. But along the way, we had to develop very good plating for the anode and the coatings, as I mentioned. So now what we're doing is part of the team is working along this path to develop this 3D copper antimonide porous electrode as a drop-in replacement for the graphite electrodes that you have in your batteries today. And then the longer-term vision is this full 3D solid-state cell. We are a very small team in terms of the company, so any development work that we do, we have to make sure can be applied to all areas of the company. Okay, so for the polymer, I'll just go very quickly. This was the biggest challenge. This took the longest amount of time in terms of the development. The polymer electrolyte has to have controllable thickness. It has to conformally coat a 3D window, a 3D electrode. The challenge here is that it has to be stable over a very large voltage range, so it has to be electrically insulating, but it has to be ionically conductive, and it has to be mechanically robust. This is not the polymer that we use. This is just a sort of a cartoon of one of our beginning pieces. But basically what we had to do was develop the methods for electrochemically polymerizing mixtures of monomers that would each have the physical properties that were needed to result in this polymer electrolyte. We use electrochemical polymerization because, remember, the polymer has to be electrically insulating. So the idea is that as you polymerize the material and it coats your electrode, it will turn itself off once you've completely coated. So this data demonstrates that. This is a current density as a function of time. In the first pulse of the electrochemistry, you get initial polymerization on the surface, which reaches a diffusion limited range. Then you let the solution rest. You pulse a second time. You see the current density is much lower because most of the electrode's coated, and in this way we can make sure it's well coated. To test the quality of this coating, we needed to develop methods that were very fast, that could let us know that our layer was perfect before going on to the last step of adding the cathode material. So what we do is we put a very small molecule in solution that has well-known electrochemical activity. So if you scan voltage and measure current, the molecule gives a signal that looks like this. Once you're coated, there should be no signal at all. We call this redox shutoff. This tells us that the coating is perfect, and then we can go on to the next step. If we see any signature of this molecule, we know there's a defect somewhere. We don't need to know where it is, we just need to know it's present. We can then put the electrode back in the monomer solution, pulse one more time, and in that way we've been able to basically demonstrate the first true 3D battery that actually stores charge and that doesn't leak current. Okay, so in terms of the polymer, what we do is we set targets for ourselves that are associated with stage gates. Again, very different from the kind of academic research I'm used to, where my students really work on understanding how things work, and sometimes the timelines we don't really pay that much attention to. In the company, we have pretty strict timelines because we've promised to meet certain milestones for our partners and for our investors. So what we do is we use our model that we use to calculate what the power density and energy density should be, and we set these lines for the physical properties we need to meet. So in this case, ionic conductivity for our polymer, to achieve a 5x power density improvement, we need to hit at about 10 to the minus 6 Siemens per centimeter. And then in thickness, we need to be at 1 micron. We've gone through many systems that did not work very well. And basically where we are today is we can achieve the target conductivities that we wanted, but now our films grow so quickly they are a little bit too thick. And so now we're working on making the polymer layers thinner while maintaining the ionic conductivity. And this is how we drive toward the performance that I showed you that we calculated. So just a couple of pictures and then a quick description of where the company is today. This is a low resolution scanning electron microscope image of our 3D battery. And basically what you're looking at is the cathode slurry and the aluminum mesh current collector on the cathode side. If you freeze this in liquid nitrogen and crack it, you can see a cross section. And here you see the copper foam, which is hollow, copper antimonide, coated anode, our polymer electrolyte, and then our cathode. And I like to show this image because I just want to show you that the battery does exist in the real world. It's not simply a calculation. Okay, so the company was founded in 2009. Again, I mentioned that the university is really trying to encourage faculty to try to spin out their ideas, and in this way the university is really trying to capitalize on the intellectual property that faculty were developing. And I'll be very honest, the only reason I started the company was because I was an assistant professor and I really wanted to buy a battery cycler. And those are slightly too expensive to write into a normal National Science Foundation grant, but not really expensive enough for an instrumentation grant. There was there's a local family fund, a woman of great wealth in Fort Collins who happens to drive the sports car that I showed you on that first page. She was thinking about batteries. She invests very heavily in high-risk startup companies that have the potential to benefit humanity. And all she really cares about is creating jobs locally. And so she wanted to invest, but I could only take the money if I started the company. Now we have grown pretty significantly. I'm just showing you part of the technical group. The reason I'm showing you the picture is to highlight the age of the team that is working with me. We're all pretty young and had never worked on batteries before. We have 9 full-time employees now and 2 consultants, and we're backed still by private investors. Just to briefly show the highlights, I already showed you this pilot line. All of these facilities are in a new incubator space that the university built. And what's interesting is that our undergraduate students voted to use their fees to build this building, the hope being that they could help startup companies become successful locally and create jobs locally. Colorado is a very beautiful place to live, so most of our students don't want to leave. So I think it's very forward-thinking of them to try to create an environment where companies could start so that they could be hired, basically. So the way that this works is if you're a company from the university, the rent is heavily subsidized. Your employees have online access to all the journals. All the hazardous waste is disposed of exactly as if you were in the university. And you also get access to a lot of the characterization equipment that is present in the university. Now, in terms of the business, we've been pretty successful with IP recently. So we have about 22 patents that are all pending. The first was just allowed this last year. So notice that's an order of magnitude different than what Tom showed for IBM, but we are making good progress. And I just wanted to show you a picture of this first battery cycler that we bought. Remember, that was the reason why I actually started this company. So with that, I want to thank my academic research group that made all of this possible. The people that you see here are currently in my group. These are all the people that have been in my group in the past. And I want to highlight Derek Johnson, who was my very first postdoc. He first helped me build my academic lab, and now he is the director of the science and technology for my company and has helped me build that. And also to thank all these institutions for funding the academic side of this group. So with that, thank you again very much for the invitation. I'm happy to answer any questions that you have.
So we are